So again, welcome. I warned you that we might have a couple of difficulties being the first installment, but I think we're going to be pretty smooth from here. One thing that when I do a presentation I really appreciate and I like is questions. If it's not too noisy, I mean, I saw a lot of you went on mute, which I appreciate. You know, it gets a little bit noisy if everybody's off mute and you hear dishes and things clanging in the background. But if you have a question, feel free to step in and just ask the question. You don't have to do the raise your hand thing on the screen. If you like I said, please feel free to ask. I want to make sure that we answer all the questions that you have. So the topic of discussion today is solar inverter and charge controller introduction and application. So what I have found in presenting over the years is that if you come out straight with a presentation about all your fancy gadgets and equipment, quite often it gets lost in the audience on what we're really talking about as far as what these things are. So the purpose of today's presentation, this morning's presentation, is basically it's an introduction to what is an inverter and what is a charge controller. Now, to many of you, that might be very basic. That might seem overly basic, but you'll never know. You might find things here that you never thought about before. So we're going to kind of move on with that. My name's Roy Dingen. For those of you who don't know, who I guess I forgot to introduce myself. I'm senior technical trainer at Schneider. I've been around the industry doing training for quite a while. I worked back at Trace and Xantrex back in the old days for 10 years, and then some other competitors in between. So I've been doing this about 20 years. So if you have any questions about this stuff, like I said, feel free to ask, and we'll start marching forward. And if I don't hear questions once in a while, I'm going to stop to make sure that you can all still hear me. So, how do I move forward on my slide? Huh? That'll work, I guess. Okay. So, since the topic of discussion is an introduction to inverters and charge controllers, we'll start off with inverters. So what is an inverter, or what is an inverter charger, which is what we're talking about, and I'll get into detail. But the purpose of an inverter charger is to invert stored energy from a battery to run household loads and or charge the battery bank as needed from an AC source, such as the grid or a generator, which is why we don't just say inverter, we say inverter charger. So in this picture you see here, we see a couple of examples. The upper one is what we call the XW Plus. We'll talk about that to a degree. On the right side, we see something called the Connect SW, smaller, a little bit less features. We'll talk more about that. And the very bottom one there is actually an inverter that's not available in North America, but it's called the RL. It's a grid tie inverter. And I'm going to really go into depth. One of the most important things to discuss today is the differences between a grid tie inverter and a battery-based inverter. So that's not an inverter charger, but just an inverter. But we'll talk about that. Okay. So this symbol I see quite often in drawings. People will send me drawings, say, would you please approve my application for an inverter? And this is the drawing, or the symbol that I see on their schematics for a system. Now, this drawing, or this schematic symbol in its present form, really doesn't tell us much of the story. It's going to be kind of a starting point from where we're going to go with inverters and chargers and inverter chargers. And all we really see here is that the fact that there are DC connections and there are AC connections, but we don't really know what the purpose of this device is. And the reason we don't know is we have no direction. We don't know what there is for an input, what there is for an output. So if we move on and give this symbol some direction, some basic direction, we now have AC coming in and we have DC going out. So this is something that we all are probably familiar with, a converter or a charger. Converters and chargers are basically the same device, but used in different ways. But they convert AC to DC. So the differences from a functionality standpoint between a converter and a charger are listed here. A converter typically has constant voltage. You can see that there in the green. I don't know if I have a way to... Can you see my mouse out there? I'm sure you can. Let's assume you can. So an example of a converter is in an RV or a boat, potentially, where you plug into the shore power and it converts the AC at the shore power, converts that to DC to run the DC loads on board the coach or the boat. That's a perfect example of a converter. A more common one is a device that we all have that I call a wall wart, that plugs into the wall and powers your laptop, well, these days pretty much everything. I think we may have had just somebody join that isn't on mute. There's some rustling in the background there. If you could put yourself on the mute. If you have questions, please feel free to move in. I know a few other people just stepped in. To sum things up, I'm Roy Dangan, and if you have questions, please ask. But if you have any, while you're not asking questions, if you can go on to mute, it's very helpful. So again, a converter converts DC or AC to DC. We see them every day. As a matter of fact, even things like printers and things like that use a converter these days, because it's easier for a company to get a DC device through UL if you use an already approved converter, which is why we always get these wall warts with devices these days. The difference between a converter and a charger is that a converter typically has a constant voltage. It could be a 9-volt converter. It could be a 12-volt converter. It could be whatever. We'll take your 120 or 240 or 230, what have you, and convert that down to a constant voltage. And we use that for running devices. The other application for this type of device is a charger. So we're all familiar with chargers as well, I'm sure, car battery chargers, cell phone chargers. The big difference between the two is that a charger typically utilizes a multi-stage battery charging algorithm. So they may or may not have just constant voltage output. So an example of where one of these devices could be either or is in a laptop. If you have a laptop and you plug it into the wall and you have a battery, you're basically using that device as a charger. If you don't have a battery in it and you're just running the laptop off of it, well, basically you're using it as a converter. So they're one and the same. But if we look over at the right side there, my very oversimplified schematic symbol of a charger, this will become more important as time goes on here. It's basically two steps. We have AC coming in, going through a transformer. One of the beauties of AC, the reason we use it for distribution, is it's very easy to change AC voltage with a passive device called a transformer. We can step that down and run it through a solid state device, which is the top block. And that, in this case here, we're going from AC to DC. It would be a rectifier, typically a bridge rectifier. I won't get into details about bridge rectifiers, but suffice it to say, the AC power comes in, gets stepped down in voltage, gets converted to DC, and then comes out. So that's the basic block diagram of a converter or a charger. And then you can add some brains into it and come up with different voltage outputs that change to get your multi-stage battery charging if you choose. But the important thing right now, I just focus on, that's the basic block diagram of a converter or a charger, and you'll see why that's important. Now, if we change the direction here, we bring in DC and we bring out AC, we no longer have a converter, we have an inverter. A bit more complicated. We're making, actually it's a fairly simple process to take AC and convert it to DC. Like I said, for those of you who know electronics, a simple bridge rectifier can do this. When it comes to making AC, it's a bit more complicated. The early generation inverters were all what we call a modified square wave inverter. Along came other inverters that had a more true sinusoidal waveform, but all of them have to do this and make this AC waveform happen very precisely. For instance, for North America, we use 60 cycle power. So it means that this thing has to make one AC cycle every 60 seconds exactly. So it's a much more precise development process to make an inverter than a charger. In Europe, it's 50 hertz. So there's your basic, description of an inverter. But we're going to get into the different types of inverters because that's very important to understand. So If there's any screen in this whole presentation I'm doing today that is important, it's this one here, because it has an impact on the design of your system. So there are two types of inverters in the world that we use. The first type, I'll call it right now, a voltage source inverter. Another word for that is a battery-based inverter. Another word for that is a grid-forming inverter. We can also call it an asynchronous, so it's non-synchronous inverter. And it's important to note that it delivers current required by the loads. So, like a generator, think of it like a generator. A generator is a voltage source. If you connect a 100-watt light bulb to a 10,000-watt generator, that generator will deliver, as this statement says, the current required by the load. So we don't have to worry about that extra 9,900 watts of energy. It's only delivering current required. It's a voltage source, very important. It's asynchronous, which means that it doesn't necessarily synchronize to something else. So in other words, like a generator, a battery-based inverter, if you just plug it in, the output of that to a generator or to your wall socket or to another inverter, another battery-based asynchronous inverter, you will have a train wreck. You'll have two out-of-phase voltages that do not coordinate. You'll basically blow breakers, burn wires. It's a bad thing. So that's what we mean by asynchronous. It is grid forming, which means that if you connect a battery-based inverter to a battery and turn it on, you can run a load. Which means, but one thing that's important here, the top line, is it needs batteries. They do not work without batteries. So, customer says they want to have, what's important here is when the customer says they want to do battery, they want to do backup. They want their solar to work when the grid goes down. They need to have a battery-based inverter. So if we move on to current source inverter, this is what we all know as a grid tie inverter, batteryless grid tie. So the difference between these inverters is, number one, it's batteryless. So it not only doesn't use batteries, but it can't use batteries. It's synchronous, which means that not only can it synchronize to another voltage source, but it must. So it needs the grid to synchronize to. So it's not going to work without the grid, which also means it's not grid forming. It's grid synchronous. So when a customer says, I have a batteryless inverter, but I want to make it work when the grid is down, it's not as simple as bypassing some UL 1741 listing and coming up with a way to do it. It's a different type of inverter. So these customers that want to do backup have to use a battery-based grid-forming inverter. Again, they're synchronous. And the last one is very important, which we'll come to it more and more as we talk about applications. But they deliver all the current available to it. And this will become important. We're going to talk a little bit about something called AC coupling in a little bit. We're going to talk about DC coupling, and what's going to come. This delivers all current available to it is a very important function or feature or limitation or whatever you want to call it. So, for instance, if I have a 5 kW batteryless grid tie inverter, the sun is good. I've got my 1,000 watts per meter squared of irradiance. I've got nice cool panels, and that array is putting out 5,000 watts. That inverter, that current source inverter, is going to deliver all the current available to it. Not as the battery-based inverter delivers just what is required by the load. It doesn't care about the load. It's going to deliver every last bit of energy it has. This becomes important because, for instance, another thing customers will mention and say that they want to do is, what if since my batteryless grid tie inverter cannot operate without the grid, and I want it to work when the power goes out, because they just had a power outage and learned for the first time that their batteryless grid tie inverter system does not provide backup. they think that they want to just buy a small generator and tie it to the system. Now I'll do a transfer switch, tie a very small generator to the output of my batteryless grid tie inverter, and fool the batteryless grid tie inverter into thinking there is a grid. Yes, it can work. If the generator is of sufficient quality output, it can trick the batteryless inverter. The problem is it's going to deliver all current available to it. So for instance, if we did this, let's pretend we have a 5 kW generator, we have a 5 kW solar array. And on the loads that are tied to these two devices, we have 5 kW of loads running. The generator is going to back off because the batteryless inverter is going to deliver all current available to it. So it's going to deliver 5 kW. So the generator is going to basically say, well, I'm not really needed here. It's going to see the output of that grid tie inverter as sort of an anti-load. So it's going to back off its output because it can do that. Now, if the load decreases, we'll say to 2,000 watts, we have 5,000 watts available from a grid tie inverter. We have 2,000 watts of loads being run. What happens to that extra 3,000 watts of energy coming from the grid tie inverter? It basically goes back into the windings of the generator, can damage the voltage regulator, it can damage a lot of things in the generator. But it goes someplace. That's the key. It does go somewhere. It doesn't just, you can't just draw from it what is required by the load like you can in a battery-based inverter. So the gist of this whole screen is that there are things a battery-based inverter, a voltage source inverter, can do, and there are things a current source inverter can do. But there are also things that they cannot do. And so to do battery backup, in other words, when I say battery backup, to do a system that operates when there's no grid available, you have to use a battery-based inverter, a voltage source inverter. Is that pretty clear? I mean, this is a very important idea here. I want to make sure this is all clear to everybody. If there's any questions, please pipe in right now. Okay. In that case, we will march on. So, when I showed you, if I bounce back a couple screens here, let me move this out of your way. If we move back a couple screens, I go previous here, and we look at the basic block diagram of an inverter. We see that we have, I forgot to mention this earlier, the basic block diagram of an inverter is we bring the DC in, we create an AC waveform out of it using switching, which is solid-state devices, and we put it to a transformer to bring it up to our desired voltage. If you notice, it's exact opposite looking from the power electronic standpoint of our charger. So from a power electronic standpoint, these two devices are very similar. There's logic involved, and there's brains and CPUs and things that make things happen. But from a power electronic standpoint, these are very similar. So somebody years ago came up with this idea of making something we're going to call an inverter charger. And what an inverter charger is, if we look at this drawing here, we'll notice that the DC now is bidirectional. So when it comes to this whole directional discussion, the DC is directional. The AC input is one direction. The AC output is one direction. So in basic operation here, you connect an AC source, the generator, a grid, to that AC input, and use it to charge a battery. I hear that somebody else has joined. If you could put yourself onto mute, it would be greatly appreciated. Until you have a question. If you do, please ask. So the other direction here, if you have DC stored in the batteries, you can convert that to an AC output. So we call this an inverter charger. And this in your most basic form is how they work. AC input charges the batteries from a grid or a generator source. AC output goes to your loads. We're going to mess with this theory in a little bit here when we talk about AC coupling, but for now, just leave it at this. So the battery in an inverter charger is bidirectional, the battery terminals. The AC input right now is an input only, and the AC output is an output, which would be, from our previous slides, this AC output is a voltage source. So it's a battery-based output. Now, we're going to look at basically a block diagram of a specific inverter here. Uh-oh, what did I just do? I don't know what that screen is. Can I minimize that? Okay. So, if we look here, now we have basically a simplified block diagram of our XW plus inverter charger. And what you'll see, compared to the previous slide, you'll see the AC input, you'll see the AC output, but you're going to see a second input. And this is for the reason that we have two inputs is to make your wiring a little bit easier. Because if we look to the left here, the AC1 input is your connection to grid. Because remember, we spoke about it earlier and said that the AC input could be from either grid or generator. But in your typical battery backup situation, you're probably going to want both. So we're going to have an AC input going from the grid. We're going to have, that's AC1. We're going to have an AC input 2 coming from your backup generator, in case for those long power outages. Then we're going to have the AC output going to your loads. And then down at the bottom, we have our battery terminals, which remember are bidirectional. Now you'll see on the AC inputs, both of them, you're going to see a switch there that are currently in the open position. We call these the transfer switches, internal transfer switches. So what will happen is, for instance, if we connect the grid on AC1, the inverter will qualify it. It'll say, yes, I see there's an input, I see grid, and then it'll verify its quality, its voltage and frequency, and once it does that, it will close the relay, the top one there in this case of the grid, and it'll pass that energy on through the relay out to the loads and run the loads directly with the grid. Key note here is that this is not a power conditioning device, so whatever you have coming in is going to be the same thing going out. And this is the case in all battery-based inverter chargers. But the path, there's a second path that I didn't really draw here well, but there's a second path, and that path is down to the battery charger. So with any excess energy you have coming from the input that is not being used by the loads will go to charge the batteries while the grid's available. So in its typical application, the grid's available, running the loads, maintaining batteries, that grid goes out, that transfer opens, the loads are now powered by the inverter in an inverter function using energy from the battery terminals. And if there's not enough energy there, say if you have solar and such, which we'll get into more detail, but not enough, we can actually start the generator. It'll come in the AC2 input. One thing to note is that both of those inputs, AC2 and AC1, will not close at the same time, which would be a direct short. Again, two voltage sources tied together. So you can change the programming to make either one of them a default. By default, right now, the AC1 input will be your priority. So in other words, if the grid was coming in on AC1, for whatever reason you started the generator, no damage would be done, but that input relay would not close. It would just prioritize the grid. So that's your XW Plus inverter charger, and we're going to call this right now. Oh, did I see a question there? I think I saw a question, but I don't know how to do this. I think I saw a question come up, and I don't want to miss it. Whoever asked the question, just go off mute and ask the question, because I don't know how to find it right now.
My name is Ram. I sent that question a minute ago.
Okay.
Can you hear me?
Yes.
Okay, no, I was just, a quick question there. The bottom box which shows the DC and AC, should those be interchanged by any chance? The DC going at the bottom and the AC on the top?
No. Oh, well, yes, actually, that's a good point.
Right.
Yeah, very good point, actually. Thank you. Yeah, what I did there is I basically just drew that as a block. That was just a conversion block. No, good eye. You caught me on that one. Yes, that block there should be reversed to show AC coming in and then or DC coming in, AC going out. Thank you.
Good, thanks.
Good eye. Yes, no, that proves that you were paying attention. Thank you. So,
Thank you.
great point. This drawing should be flipped over. I'll do that. I've caught a few along the way, and nobody's ever caught that one yet. So, but other than that, I think we're pretty close to correct. So we're going to add now we're going to add a twist to the whole thing here. We talked earlier about battery-based, voltage source inverters and grid current source inverters and such, and battery-based inverter chargers. And now we're going to have something, a functionality called Bi-Modal functionality into the mix here. And if I compare this inverter charger drawing, and if I go back a few slides here, so look closely at this one, and if I go back to here, there's one difference between this, which is our standard inverter charger, and the Bi-Modal inverter charger. Notice the AC input terminal. Here we have the AC input terminal coming in only. If I come to this one now, we now have the AC input as bidirectional. And we call this, there's different names for it. We can call it, the most common term, probably in North America, is a battery-based grid tie inverter. The term I like best, but I've only really heard it used frequently in Puerto Rico, is bimodal. It's a bimodal inverter. And the difference is the AC input can actually become an output. It's bidirectional. So when we're doing grid tie battery backup, that AC input can also sell excess energy to the grid. And I'll get into that with more clear system drawings here pretty soon. But suffice it to say that is there's a major difference between a bimodal inverter and a non-bimodal inverter or a standard inverter. And an example using our products, which we're going to be going into in future webinars. As a matter of fact, tonight or this afternoon, I'll be going into the XW Plus. But one of the comparisons to our XW Plus inverter and the Connect SW inverter is the XW Plus inverter has the ability to become a bimodal inverter. It can sell excess DC back to the grid. I'll talk about that more in drawings, so you'll see what I mean by that if you don't. The CSW or Connect SW inverter, a smaller, less featured device, it's got some really cool features in its own right, cannot be bimodal operation. So you cannot do battery backup grid tie from a DC source, which we'll talk about that in more detail. So here we have, again, basically that same drawing. Here we have the XW Plus now, bimodal. So this is what we call this grid support or grid tie enabled, which is what makes it bimodal. So that AC input now, the only difference between this and the slide that looks similar on the standard one is that the AC input is bidirectional. I'll get into some more system drawings that will make more sense of all that and how that works. But suffice it to say, that's the only difference. You program the XW Plus to make it bidirectional. So we're going to get away from inverters for just a second, and we're going to talk about charge controllers. And then after charge controllers, we're going to come back and talk about systems and how they work together. So I think and hope that we have a pretty good basic understanding of battery-based inverters, grid tie inverters, the difference between bimodal and non-bimodal, this will become more clear when we get into systems again. So if you don't quite have it, don't worry, it'll become more clear. But the solar charge controller section is pretty short. Solar charge controllers are pretty simple. Matter of fact, the first thing I worked on when I came into the industry in 1995 was this device right here. And it's a product that we still make at Schneider, and it's called the C-Series charge controller. This is my first job in the industry. And I was testing them, and I didn't know what it was. So I asked my boss one day, I said, okay, I'm testing these C40s. What are they? So they sent me off to the tech support department to train me up on just what I was working on. And this first sentence here was the first thing I learned. The tech support guy told me this. He said, the primary purpose of a solar charge controller is to prevent overcharging batteries and provide optimum charging algorithms. So that's what a solar charge controller does, and we're going to talk about the different types of them. And these are the four, well, there's actually a few more models. These are the models that we offer currently. The second functionality of a charge controller, a solar charge controller, is this bottom line. Maximum power point tracking charge controllers, the two top units, the MPPT 6150 and MPPT 8600, they have a secondary purpose. And they are to optimize the available energy from the array, and we'll talk about how that happens. But the two bottom units are something we call a PWM charge controller. The two top units are something we call MPPT charge controllers. And I'm going to talk about next what the differences are between the two. So when you get to where you're choosing a charge controller, you'll hopefully know more about what charge controllers are. So we're going to start back in the beginning of time from solar terms in charge controllers. And this is something that Trace Engineering, which subsequently turned into Xantrex Technologies, which then turned into Schneider Electric, made originally called a C30. I can't find any pictures of this device, so I didn't have it on that front page. But really, this is the first generation of charge controller, and I call them a relay-driven charge controller. So if you look at it, we have a solar panel. And back in those days, it was all 12-volt nominal solar panels, which put out about 17 volts open circuit, going through this device, this C30 charge controller, onto the batteries. So it was a very simple device with two potentiometers to adjust, one called HVD, or high voltage disconnect, and one called low voltage reconnect. So what it would do is when the battery voltage got up to a prescribed setting, we'll just use 14.4 as an example, it would actually just open up the switch and disconnect the solar array from the batteries. Very simple device. When the voltage fell again to something we programmed called the LVR, it would then reconnect. And the reason for having those two is to give us a little bit of hysteresis. If you had the same set point, for instance, let's say, as an example, if we set these two at exactly the same point, we'll just say 14 volts, it would open and close at such a high rate of speed, it would actually burn the contacts up. This was a mechanical relay. So these two set points, high voltage disconnect and low voltage reconnect, give us some hysteresis. One of the drawbacks of this type of device was that you must use the same voltage panel array as your battery voltage. So in other words, if we had a 12-volt system, it had to be a 12-volt nominal panel. If we had a 24-volt battery bank, this had to be either two 12-volt panels in series or a 24-volt module, because this does not change the voltage of the output of the array. It's just a switch. So another drawback of this system was that after the unit would reach high voltage disconnect, the battery voltage would fall, we'd be running off the loads and not using the energy coming from the array at all. It would just be basically sitting there wasting until we went to the low voltage set point. So it wasn't a very efficient method of charging. We couldn't hold the battery voltage at a specific point. So we had no real ability to do a very smart charging algorithm. We could just disconnect. The only thing we could do, back to the primary purpose of a charge controller, is prevent overcharging the batteries. All it could do. So next comes something I call the second-gen charge controller. You may have heard the term a PWM charge controller. You see this a lot when you look in solar equipment catalogs, you'll see PWM charge controllers. We currently offer two varieties. We offer the C12, which is on the left, which is a 12 amp, 12 volt charge controller. And we offer the C series, we call it. The one showed here is either a C60 or a C40. The C40 will operate 12, 24, or 48 volt battery banks at 40 amps. The C60 will operate 24 and 48 volt battery banks at 48 volts. And we also have a C35 that will do 35 amps at 12 or 24 only. But a key to the function of these are the first two statements here. They do not change the voltage, and they don't change the current. They're just a switch, but a high-frequency switch. So if we look at the left side here, this is sort of a representation of how they operate. This is a 1/10 of a second snapshot in time. And we call this pulse width modulation. And what it is we vary the amount of time the switch is turned on versus turned off. Now, this is not done with a mechanical switch. This is done with an FET switch. So we're not going to worry about burning out contacts, so it can be much faster. So the switch speed actually is 100 times per second, so it's 100 hertz. So it changes the duration the array is connected by means of varying the on versus off time. So, for an example, if we're trying to maintain a target voltage of 14.4, and we'll just say that we have 2,000 watts of solar coming into the batteries, and the batteries are full. So the batteries are full. We have 2,000 watts of solar coming in and no loads. The switch would just be off because we would need no more solar to maintain battery voltage. But what if we increased the load up to match? So we increase the load now to 2,000 watts. Now we'd be going down to this scenario. The switch would be on constantly. So we would deliver that 2,000 watts basically directly to the load, you could think of it as, because the batteries are full. But if that load decreased to 1,000 watts, so we only needed half the energy from the array, we could do that by means of changing the on versus off time. 50% of the time off, 50% of the time on. Again, we can't change the voltage, we can't change the current, but we can change the kilowatt hours or watt hours delivered to the battery by means of this off time. We call that pulse width modulation. So this results in a fuller battery because we don't have to just turn it off once the batteries are full. We can actually match the loads, but it also enables multi-stage charging. So now what we can do is we can vary this pulse width to maintain a target voltage like a bulk voltage. And for a 12-volt battery, that might be 12 or 14.4 volts. We can maintain that 14.4 volts by means of pulse width modulation, even with loads coming and going. And then at the end of the absorption time, which is by default on these devices 1 hour, then it will drop into something called float. This is our 3-stage charging. We bring it up to a higher voltage, then bring it down to a lower maintenance voltage. So the 3 stages of 3-stage charging are bringing it up to bulk, number 1, holding it at bulk voltage, we call that the absorb time, number 2, and then after that period of time, drop to something called float, which results in a fuller battery because the batteries like to be charged a little bit hotter to begin with, and it decreases your water usage by dropping down to a float or maintenance voltage. So a much better charging algorithm by using this thing we call pulse width modulation. Now, the one drawback, or one of the drawbacks to this system, I mean, it was much better than the first one, but the array voltage must match the battery voltage. So just like the relay-driven charge controller, we still have to match 12 volts to 12 volts because of the first two statements. It doesn't change the voltage and it doesn't change the current. So if you connected a 48-volt nominal array through this to a 12-volt battery, you would basically just be wasting energy. So it wouldn't. So 12 volts in, 12 volts out. 12-volt nominal in, I should say. So that's a PWM charge controller. They're still used frequently. We actually sell an ungodly number of these worldwide. Very robust. They've been around since the mid-90s. Very efficient. And less expensive. We see them a lot in developing nation applications, simpler applications. The C12 that you see on the left is actually a very cool device. You can also use it as a load controller. So it has 3 sets of terminals: battery terminal, array terminal, and a load terminal. So you can run a 12-volt load like a light. So for instance, if you use it as a bus stop lighting controller, it would charge the batteries, maintain the batteries full, or do the best it can, depending on the array. And then when it measured the array voltage dropped to below 3 volts, it would assume that it's nighttime and then turn on the lights, and then protect the batteries from over discharging by turning off the lights if the batteries go too low. The C40 can also be used as a load controller, not with the lighting controller function, but it can actually be used as a 40 amp, 60 amp, 35, depending on the model, load controller, which a load controller is really a low voltage disconnect for DC loads to protect the battery. So in other words, if I want to run my DC refrigerator off of one of these, I could set it so that it would never allow the batteries to fall below, we'll say, 11 volts. We could set it for instance. So if the batteries go down to 11 volts, it would turn off the loads, and the loads would be limited by the wattage or the amperage rating of the controller. So pretty good device still. But the next phase in charge controller evolution is something we call MPPT, Max Power Point Tracking. And originally there's a lot of advantages to it. And what it does is it finds the maximum power output of the voltage of the array to increase array output wattage. So if we look at a nominal 12-volt module, a nominal 12-volt module puts out about 17 volts and open circuit, and its max power voltage, or VMP, is really it's kind of tailored to be above battery voltage, desired battery voltage, on a hot day. So, for instance, a 12-volt module might have a VMP of 15 or 16 volts, which is above what you'd want to charge a 12-volt battery. Now, when it gets cold, and the reason for that is on those very hot days, that VMP, that voltage at max power, will fall with higher temperatures. So we always want voltage to be above. Now, in a colder climate, that VMP can rise, which gives us extra energy. But in a non-power point tracking charge controller, we can't utilize that extra energy. It gets wasted because we have to go 12-volt module in, 12-volt module out. So what a power point tracking charge controller does, it allows the array to operate at a different voltage than our target battery voltage. So in other words, if the VMP, or max power voltage of an array, is at, we'll say, 18 volts, and our desired charging voltage is down at float at 13.2, it can operate that way by means of DC to DC conversion. So now we have 17, 18 volts coming in at a given amperage. We convert it down to the lower voltage, which brings the amperage up, and of course better battery charging, so more efficient harvest of the array. So that allows us to operate the array at different voltage than the batteries because of this DC to DC conversion, which means now, for instance, the part numbers of these two controllers we see on the right side, the one on the left is what we call the MPPT 60-150. And what those numbers mean is that it can put out 60 amps continuous DC amps, and it can have a maximum maximum DC input voltage of 150. So we can basically operate, I guess that'd be probably a 72-volt nominal array, I believe. It depends on your climate. So what we have actually a design tool on our website called Connects Designer that allows you to go in and do your string sizing. I'm not going to go into that today. But we can do string sizing and come up with the maximum number of modules you have in series, which bumps up your AC input or DC input voltage, and allows you to run farther away from the controller as well. So now that we go to this 150 volt maximum input, we can decrease our wire size on the array to charge controller input size, saving copper costs. We can operate at the max power point of the array, which also makes for better harvest. and maybe even most importantly, allows us, these days it's hard to find 12 volt, 24 volt, 48 volt modules. We're all dealing for the most part with grid tie modules, which are 40 volt open circuit, and allows us to use grid tie modules in an off-grid application for battery charging. This is probably the biggest advantage. Now the controller on the right there it goes even higher. We call that the NPPT 8600, which means it has an 80 amp output maximum at a 600 volt input. So one of the uses for this, now 600 matches our standard grid tie inverters that we all deal with. If you're going to change a system from a pure grid tie and want to go to a battery-based system, you can use the 600 volt controller without rewiring your array. So it gives you that advantage. And of course, a fourfold increase in maximum voltage on the input side gives you even smaller conductors on that DC input side, saving even more copper costs. Actually, anybody who's going to be at the Midwest Renewable Energy Fair, I'm going to be talking, I think we're going to be talking, we'll be talking about the cost savings of going to a 600 volt controller over 150 volt controller in terms of copper and things like that. So that's what a max power point tracking charge controller is, and that's the two that we offer. So hopefully we all have a better understanding of what a charge controller is and the different types that people use, because the next step, we're going to tie it together. And we're going to talk about systems and how these things get used together. So in its most basic form, we have here what we call the XW plus inverter. What we have on the right side there with that red arrow, actually in all these drawings, I call these my cartoons, so please do not try to turn them into your building inspector or your electrical inspector as a system drawing, because they do not have sizing requirements. I've actually had somebody do this, which is why I said that. What we show there on the right side is your AC output, and it's going to a load center. And then we see that going on to running household loads. Down below, we see batteries. In the case of the XW Plus, that would be a 48 volt nominal battery bank. Blue arrows are going to be DC, red is going to be AC throughout these cartoons. So this is our most basic operation of a battery-based inverter. Inverts stored energy from battery to loads, needs a charging source here. That's the problem. The limitation of this particular system we see here is that once the batteries are dead, the system will shut down. So there's some limitations here that we're going to have to overcome, and we'll add them in the next slides. So now, our basic, and this is how it's been done for many, many years, our basic off-grid PV and generator system. So stored energy in the battery is inverted to loads assisted by the solar, and generators started either manually or automatically based on need. So here we have our PV modules going through our controller on the bottom. I'm showing here an NPPT 150. We're charging batteries, and that battery energy has the ability to be converted here in the inverter, running loads. I call this a sub panel, and you'll see why in a little bit, but it's basically your load center. Running and I call those backed up loads, but again, here I'm getting ahead of myself. These are just our loads in an off-grid system. And then we have the potential for connecting a generator for those times when we have insufficient solar resources to run the load. So we can run the generator, starting it based on state of charge of the batteries. We can start it on the voltage of the batteries. We can start it based on loads. So for instance, if we see a very large load come on, we can say, well, we think we're going to need the generator. Or we can start it based on time of day. We can do lots of this in programming. But that's our basic. And we're going to come into something here I'm going to call AC versus DC coupling. And this right now, many of you may have heard that term. Some of you may know what it means. But basically, what we mean by that, the term coupling means tying something together on a bus. So here, we see the generator, the inverter, the loads tied together on this AC bus, basically. And we see the PV, charge controller, and batteries and the inverter tied together on the DC side. But in the solar industry, when we say AC coupling or DC coupling, what we mean specifically is that the array is tied through its regulation to the batteries, or really correctly, you might say, to the DC bus. So this would be a DC coupled system, basic off-grid. So now, if we add to this basic DC coupled system, if we add to this the utility, so now in normal operation, the loads are powered by the grid via the inverter's internal transfer switch, which I showed you earlier. I don't show it in this drawing. But the grid is available. It's running loads on your main panel. These are your big loads that are not backed up. These are things like your hot water heater, your, it's another bad example of a load, an electric range, electric furnaces, things like that. Typically, people don't want to back, well, typically people can't afford to back them up because it gets very expensive. So we pass through the inverter onto a sub panel, and these are your backed up loads. This is where you will have, in my ideal house, I would have one outlet per room and a refrigerator and some basic lighting and your TV. Typically low energy loads and required loads, aquariums, things like that. So when the grid's available, power is available to both the main panel and sub panel. When the grid goes out, this goes dead. The internal transfer switch opens up. We power the loads on our backed up load center only using the batteries. Right now, we don't have any solar in the system because it's not absolutely required. Now, you could also add a generator to this, or you could add solar. We'll get to those later. When the grid fails, inverter energy is stored to the sub-panel loads only. And one of the things that people try to get around, and I understand it, I mean, one of the most complicated parts of doing a battery backup grid tie system in anybody's application, I mean, in any home and from any inverter manufacturer, is the fact that you have to pull this sub-panel. But keep in mind something. This inverter, we didn't talk about that transfer switch in much detail earlier, but that transfer switch is rated at 60 amps, 48 continuous. So, if you were to put this inverter upstream of the main panel and try to feed the whole house, you would have a bottleneck. Now, we can use multiple inverters, but generally speaking, in my opinion, a good battery backup system, basically you have your basic requirement loads and not the big ones. It does require pulling a sub panel, which I know is electrician time. It's, you know, $1,000-$2,000 in labor to pull a sub panel and bring those loads over. And it's never simple because the house was not designed originally for that. I understand that, but it is the best way to do it. There's ways around it. If you really have situations where you can't deal with that, I'll give you my phone number at the end. And if anybody has any questions, you know, going forward to email me, I'll put my email and phone number up. You know, feel free to contact me when it comes to specific applications. We can talk about that. But note that the loads on the main panel are not energized during a power outage. So back to the discussion of grid or current source versus voltage source inverter. Think of the AC input here. This is AC1. Think of it as a current source inverter. When the grid's available, it has the ability to sell back. That's why this arrow is bidirectional. But when the grid goes out, it's not a voltage source, so it doesn't put out voltage. So it's not going to power these loads here. So now, if we're going to add everything to this system, well, my little recorder button keeps overlapping me. If we add everything into this now, what we have here is we have, oh, what happened there? Okay. We have the grid coming into the main panel, passing through the inverter, running the sub-panel loads, running the backed up loads. We have residential loads running on the main panel, the grid. The grid goes out. The switch opens. We run the sub-panel loads off of batteries, which are now assisted by solar. If there's not enough solar to run the loads in a backup situation, the generator can come on and run the loads. One thing to note here that's important, if there is excess PV coming in, for instance, let's say we have 5 kW coming from the array, and we have only 2 kW of loads on this sub panel. That excess 3 kW can actually come back out the AC input, power loads on the main panel, or even if there's no loads there, pass on through to the grid. So we can do grid-type battery backup in this application here. So excess PV is sold to the grid when available by the inverter. The loads on the sub panel are powered with stored energy in batteries when the grid goes out, assisted by PV. The generator is started manually or automatically as needed, of course only when the grid is out. The loads on the main panel are not energized during a power outage. Now, one thing you could do a little bit differently here, if you have a large enough generator, and I've seen done quite often, is as opposed to running the generator into the AC2 input, you can actually do a transfer switch, and most people that already have a generator have a transfer switch already, powering the main panel. In that case, when the grid goes out, the generator can start, power the main panel loads, and while the generator's running, charge the batteries and the sub-panel loads, then you can turn off the generator and run just your sub-panel loads. So for instance, we'll say that we had the washing machine and dryer on the main panel. You could start the generator manually, run those loads and top up your battery at the same time, shut off the generator to save fuel, and still run the rest of the household load. So there's ways around things. There are more ways to do this than we could cover today. So we talked about DC coupling. DC coupling was basically tying, whoops, I'm sorry, I got ahead of myself there. DC coupling was tying, oh, it says no grid up there, was tying the array to the batteries via the DC side. Now, AC coupling is a little bit different. So what we see here is a grid tie inverter coming into the sub panel. So let's go, if we go back to that earlier slide that I said was important about, different functionalities of inverters, this battery-less inverter needs a grid source to synchronize to. So in this case here, think of this sub panel as a grid. We have the battery-based inverter providing a sync signal for the grid tie inverter. And we can run loads, and we can utilize this energy. But there was one thing that I said that is important, and that is a grid tie inverter will put out whatever it has available to it. So we have to come up with external ways of limiting this output when the loads are low and the batteries are full. So if the loads are low, the batteries are full, we need some way to throttle back the inverter. So there's basically 3 ways of doing it. You can use a voltage control switch on the battery to disconnect the grid tie inverter. We're not going to go too deep into this today. You can use what we call a diversion load, which is a diversion load. What it is basically connected to the batteries and will bleed off any excess coming in that is above and beyond what it needs to keep the batteries full. But you have to be careful with that because the diversion load must be larger than the potential output of this array connected to. There should be an array connected to this. I ran out of room. Or in the case of if you use Schneider inverters, we can actually on both grid tie and the battery base, we actually can change the frequency output when the grid is down, which is a signal to the inverter to slow down. So if the batteries are full, the loads are low, the grid is out, of course. The XW Plus, or the battery-based voltage source grid-forming inverter, can change its output frequency up, which this inverter will see as a signal to slow down. So we're going to force it to limit its output. It's not going to limit it based on load. It's going to limit it based on the signal from the output. So that's about as deep as I'm going to go into AC coupling, but just note that we can do this with these inverters. So the battery charge regulation is not provided by the inverter charger. It's basically provided indirectly by something we call frequency shift. So these AC coupling and DC coupling things are not mutually exclusive. we can do both. We can do the grid coming in with a generator running loads. We can do backed up loads with a sub panel. We can bring in a grid tie inverter into the sub panel to do AC coupling with the XW Plus. We can do a DC controller coming into the batteries to do DC at the same time and manage all these devices. I'm not going to cover sizing today. So we couldn't, there are limitations on how much one inverter can handle from either or both sides. I'm not covering that. But in the DC coupling, the array interfaces to the system via the charge controller, the AC coupling, the array interface to the system via a grid tie inverter on the AC bus. The AC and DC coupling are not mutually exclusive and can be used together in the system. And excess AC from both here and from here can be, can be sold back to the grid. So that, I went over about 4 minutes only. That is what I have for today, or for this morning. On this afternoon, I'll be talking at 5 o'clock Pacific time, I believe it is. Be talking about the XW Plus inverter in more detail, just the inverter itself. Is there any questions that anybody has?
Hi, Ray. I'm just going to chime in. Just to clarify on your last point, the session that we have for 5 p.m. this afternoon is basically just the second session of the same topic for those that couldn't attend this one. So the session that will be going into XW Plus, that will be on Thursday.
Got it. Okay. I thought that's what it was, and then I double-checked, and it wasn't. I thought it was. Anyway, okay. No yeah. What I'd like to do, but I can't do it here, and I should have actually. Apparently, I don't have the ability to edit my slides while I'm in this mode. My thoughts on the new Tesla battery. Actually, while I'm doing this, can everybody see the sign, the thing that says down below says notes? So if I type in my email address, okay, can everybody see that? Does that show up on your screens? Yeah, okay, good. Okay, yeah, if you have any questions, specific stuff, feel free to call me, email me, what have you. Actually, usually calling is almost better. I like talking. The Tesla batteries, that's an interesting one, and I don't know too much in detail. I mean, I know about lithium-ion in general. Lithium-ions are, they can handle many more cycles. They can take a very much quicker charging, and they can handle much lower levels of discharge. So they potentially are the future. Will it be Tesla or will it be somebody else that really brings them to the forefront? Well, Tesla has, they got behind them, they got the car and everything else. So, it's hard to say. I don't know. The batteries themselves right now are, they really like to be in 400 volt applications, which is a bit of a difficult thing to do, currently to code. If you have a solid container that's UL listed and the batteries are contained within and people can't get to it, you can do that. So you almost have to build this as a unit. So for right now, I think it's probably coming. Hard to say. Any other questions at all? Well, I think I'm going to stop my recording here.